Radiative forcing from Wikipedia, a learning video. Radiative forcing or climate forcing is the difference between insolation, sunlight, absorbed by the Earth and energy radiated back to space. The influences that cause changes to the Earth's climate system, altering Earth's radiative equilibrium, forcing temperatures to rise or fall, are called climate forcings. 2. Positive radiative forcing means Earth receives more incoming energy from sunlight than it radiates to space. This net gain of energy will cause warming. Conversely, negative radiative forcing means that Earth loses more energy to space than it receives from the sun, which produces cooling. Typically, radiative forcing is quantified at the tropopause or at the top of the atmosphere, often accounting for rapid adjustments in temperature, in units of watts per square meter of the Earth's surface. Positive forcing, incoming energy exceeding outgoing energy, warms the system, while negative forcing, outgoing energy exceeding incoming energy, cools it. Causes of radiative forcing include changes in insolation and the concentrations of radiatively active gases, commonly known as greenhouse gases, and aerosols. Almost all of the energy that affects Earth's climate is received as radiant energy from the sun. The planet and its atmosphere absorb and reflect some of the energy, while long-wave energy is radiated back into space. The balance between absorbed and radiated energy determines the average global temperature. Because the atmosphere absorbs some of the re-radiated long-wave energy, the planet is warmer than it would be in the absence of the atmosphere. See greenhouse effect. The radiation balance is altered by such factors as the intensity of solar energy, reflectivity of clouds or gases, absorption by various greenhouse gases or surfaces, and heat emission by various materials. Any such alteration is a radiative forcing, and changes the balance. This happens continuously as sunlight hits the surface, clouds and aerosols form. The concentrations of atmospheric gases vary and seasons alter the ground cover. Solar forcing. Radiative forcing, measured in watts per square meter, can be estimated in different ways for different components. For solar irradiance, that is, solar forcing, the radiative forcing is simply the change in the average amount of solar energy absorbed per square meter of the Earth's area. Since the Earth's cross-sectional area exposed to the Sun, R2, is equal to 1/4 of the surface area of the Earth, for R2, the solar input per unit area is 1/4 the change in solar intensity. This must be multiplied by the fraction of incident sunlight that is absorbed, F equals 1R, where R is the reflectivity, albedo, of the Earth. The albedo is approximately 0.3, so F is approximately equal to 0.7. Thus, the solar forcing is the change in the solar intensity divided by 4 and multiplied by 0.7. Likewise, a change in albedo will produce a solar forcing equal to the change in albedo divided by 4 multiplied by the solar constant. Forcing due to atmospheric gas edit. For a greenhouse gas, such as carbon dioxide, radiative transfer codes that examine each spectral line for atmospheric conditions can be used to calculate the change F as a function of changing concentration. These calculations might be simplified into an algebraic formulation that is specific to that gas. For instance, a proposed simplified first-order approximation expression for carbon dioxide would be: radiative forcing is a useful way to compare different causes of perturbations in a climate system. Other possible tools can be constructed for the same purpose, for example Shine et al. 13. Say ... Recent experiments indicate that for changes in absorbing aerosols and ozone, the predictive ability of radiative forcing is much worse. We propose an alternative: the adjusted troposphere and stratosphere forcing. We present GCM calculations showing that it is a significantly more reliable predictor of this GCM surface temperature change than radiative forcing. It is a candidate to supplement radiative forcing as a metric for comparing different mechanisms. In this quote, GCM stands for Global Circulation Model, and the word predictive does not refer to the ability of GCMs to forecast climate change. Instead, it refers to the ability of the alternative tool proposed by the authors to help explain the system response. Therefore, the concept of radiative forcing has been evolving from the initial proposal, named nowadays instantaneous radiative forcing, IRF, to other proposals that aims to relate better the radiative imbalance with global warming, global surface mean temperature. In this sense, the adjusted radiative forcing, in its different calculation methodologies, estimates the imbalance once the stratosphere temperatures has been modified to achieve a radiative equilibrium in the stratosphere, in the sense of zero radiative heating rates. This new methodology is not estimating any adjustment or feedback that could be produced on the troposphere, in addition to stratospheric temperature adjustments. For that goal, another definition, named effective radiative forcing, has been introduced. In general, the ERF is the recommendation of the CMIP-6 radiative forcing analysis, although the stratospherically adjusted methodologies are still being applied in those cases where the adjustments and feedbacks on the troposphere are considered not critical, like in the well-mixed greenhouse gases and ozone. Recently, a new methodology named radiative kernel approach allows to estimate the climate feedbacks within an offline calculation based on a linear approximation. The Intergovernmental Panel on Climate Change, IPCC, ERF report defines radiative forcings as, radiative forcing is a measure of the influence a factor has in altering the balance of incoming and outgoing energy in the Earth atmosphere system, and is an index of the importance of the factor as a potential climate change mechanism. In this report, radiative forcing values are for changes relative to pre-industrial conditions defined at 1750 and are expressed in watts per square meter.